Okay, I'm going to switch now to noteworthy, and I want to review some of the things we talked about the last time. And we'll pick it up from there. I'll take any questions you have as well, and hope problems that are bothering you and so on. So let me share my content. Okay, so I want to backtrack a little bit to the moment generating function. Which was defined to be e to the tx, the expected value of this exponential, which is kind of a weird kind of thing. And in fact, let me switch to black. We showed that in the discrete case, this is just equal to e to the t x of I times the product of the corresponding probabilities. And the moment generating function generated all moments. So in particular, the first derivative of the moment generating function was the mean. Derivative of the moment generating function was e of x squared, which I think we called u2. And the moment generating function had a very important property, namely if x and y are independent, the moment generating function for their sum is equal to the product of the individual moment generating functions. I think I called this a reproductive property. And this property is very useful in finding the mean and the variance of any distribution. And then the last time, I introduced the binomial distribution. I want to redo that one again another way. So we have some random variable x, and we perform an experiment n times. Sometimes we say n trials or n outcomes. And each trial or each outcome can be classified as success or failure. Each trial is an independent event, and the probability of success on every single trial is the same as little p. Then I showed the other day that if x is the number of, if I want to know the number of successes, the probability that x equals k just turns out to be, I'm assuming I do the experiment n times, n choose k, p to the k, q to the n minus k, where q is the complementary probability of failure. And that's the basic result of the binomial distribution. I also showed that for the binomial distribution, e of x turns out to be n times p. V of x turns out to be n times p times q. And the moment generating function was, I think it was p e to the t plus q to the nth power. Those are the properties of the binomial distribution. And you don't have to memorize these properties. You give them to you right in the book, and I'll provide them for you in the exam. Okay. Now, I want to show you that this information that I just summarized, I can get a very, very simple way. If you think about a binomial experiment, X is the total number of successes. So what I could do is I could define X sub I to be a 1 if I have success, and I define it to be a 0 if there's a failure on the ith trial. I just want to show you I can get all this information again very, very simply. Then, if X is the total number of trials, is the total number of successes, I'm sorry, I can write X is equal to the sum of these indicator random variables. We've already shown that for any indicator random variable, E of X sub I is 1 times P plus 0 times Q, which is P. E of X sub I squared is 1 squared times P plus 0 squared times Q, which is also P. So D of X sub I is P minus P squared, which is PQ. Now, note the following. That E of X is equal to E of X1 plus all of these, which gives me P n times, which is the same result I had up here. And by independence, V of X is equal to V of X1 and so on, which again is n times P times Q. And if I wanted to find M of X sub I, that would just be P e to the T plus Q. And therefore, M of X is the product of all of them, which is P e to the T plus Q to the n power. So we can actually get the results for the binomial distribution another way, using independence, which is a very powerful trick, by the way. Now, it is a very useful result. Let's look at an example. Were there any questions on the homework about the binomial that anybody had in particular? No, okay. So let's suppose, here's a problem that was on the exam a year ago. Suppose we have 10 questions with parts A, B, C, D, and somebody guesses. Determine the probability they get us a 70%. How do we do that? Anybody? Notice in this problem, n is 10, If I guess right, that's success. If I guess wrong, that's failure. Okay. The probability of guessing right on any problem is, there are 4 choices.
1
out of 4, all right?
over
70, how many questions do I have to get right? For 10 questions, they're each worth 10 points. I got to get 7. So the question becomes, what's the probability that x equals 7? Okay. So there are 10 questions. I need to get 7 correct. The probability of success is 1/4. So I need 7 correct and 3 wrong. This would be the answer to the problem. You'd work this out with your calculator. This would be the probability of getting 7. What's the probability of getting at least a 90? Well, we got at least a 90, you either need 9 right or 10 right? To get 9 right means 10 choose 9, 1/4 to the 9th, 3/4 to the 1st, plus 10 choose 10, 1/4 to the 10th, and then of course this would be to the 0 power, which is 1, and this would just be 10 over 4 to the 10th, plus 1 over 4 to the 10th, and look at your calculator, and that will give you the answer. If somebody were guessing, what grade do you expect they would get? What's their expected grade? Well, there are 10 questions. Probability n times p. You would get how many questions right? The expected number right would be what? 2.5 questions. And that would give you a grade of 25%. So if somebody just guessed on an exam like this, they would get a 25%. That's the expected grade. Anybody have any questions about the binomial distribution? I give some more creative problems within the text. I give a problem about ESP or whatever. But the basic idea is the same. How do you recognize a binomial distribution? There are 3 features. Each trial is success or failure. Each trial is an independent event. And the probability of success is always the same for every trial. That any distribution that has this property is a binomial distribution. Very important distribution. Anybody have any question about this?
Professor?
Sorry?
I have a question. Are we going like on the exam or not?
Yeah, we'll go over the exam, not today. Maybe I'll record a separate session just to go over the exam.
Okay.
Okay, but I'm thinking about just recording a separate review and give you a link for it.
Okay, thank you.
That was Nadia, right? Okay. Next distribution. One we've talked about before. The hypergeometric distribution. There's really nothing new here, but we just want to make some highlight. So consider the following. We have an urn with I want to use the same notation as the text. Where okay. I have an urn. And in my urn, I have R red balls and N minus R other balls. And I choose little n balls without replacement. So the problem might be, what's the probability that I get exactly R red, say K red balls? Let me say it differently. Again, I want to use the same notation we used here for a reason. Remind me, I want to do another example on binomial. I forgot the specific example I wanted to do about that. Okay, in this example, though, let me come back to this for one example, okay? Because I want to do another example that shows up a lot. We know for the binomial distribution, the moment generating function is P e to the t plus q to the nth power. So this is a binomial, which this is an example. This is the moment generating function of the binomial distribution that has probability of success P, and it's done n times. So I gave the following problem with that. I say, suppose m of t is equal to 1 over 81 times 2 e to the t plus 3 to the 4th power. And the problem is to find P of x equal 2. Okay. Now, the first thing I want to observe is I bring the 81 into the parenthesis. I mean, I'm being a little tricky here. 81 is 3 to the 4th power. So I can rewrite this as 2/3 e to the t plus, this is 3 to the 4th. Something's bothering me. Oh, I'm sorry, this was a 1. Plus 1/3 to the 4th. So the first thing I did was transform this by observing that 81 is 3 to the 4th power. And now this looks like a binomial distribution with n equal to 4. P is 2/3, and Q, of course, is 1/3. Therefore, the probability that x equal 2 is 4, choose 2, 2/3 squared times 1/3 squared And this will give you the answer. So given the moment generating function, we can actually determine information about the probability distribution. Because the moment generating function uniquely determines the probability distribution. So once I gave you this moment generating function and I rewrote it, I recognized it was the binomial distribution. I was able to determine the necessary probability. Okay. So now let me go back to the hypergeometric that I didn't know about. I had forgotten this problem, but this is a problem that shows up a lot. I've seen it on quizzes, I've seen it on exams. I wanted to make sure you knew how to handle it. Okay, so again, I have my urn. I have R red and N minus R other balls. And I choose little n without replacement. Let x equal to the number of red balls. So the probability I'm asking, what's the probability that x equals I? Well, there's nothing new here. If x is I, it means from the red balls, I'm going to choose I. From the remaining balls, I choose the remaining balls, n minus I. Over the total number of balls I can choose n from n. We've done this problem many times before. There's nothing new here. But this has a name. I don't know why I got this thing. Maybe it has to do with more advanced mathematics. This is called hypergeometric distribution. And we notice the sum of the numbers on top always equals the numbers on the bottom. And this makes sense, by the way. I could be 0, 1, 2, up through n. We've done examples like this before. As a simple example, let's suppose we have a 6 red, 5 blue, and you choose 4. What's the probability that the number of red is 4? Or 3? X equal number of red. The probability that x equals 3, that there are 3 red, well, that's easy to get. I choose 3 red from the 6, which means I choose 1 blue from the 5, over 11, choose 4. So there really is nothing new with respect to this kind of problem. I just want to make some observations and tell you an interesting result or two. So let's go back and let's look at this urn. So I have R red, n minus R others. I choose n without replacement. So I just showed you a moment ago that the probability that there are x equal I means from the red, I choose I. From the remaining balls, I choose little n minus I. Over and choose n. Now, there are 2 questions one can ask, actually 3. It turns out there's no simple formula for the moment generating function. Well, let's suppose I wanted to find one. For example, I just want to point out it's not simple. Okay. That is, if I look at a typical example, let's suppose I have 3 red, 4 blue. I choose 3. And X is equal to the number of red. Well, I can get no red, 1 red, 2 red, 3 red. The probability of getting no red would be what? These are all blue. It's 7-3. The probability of getting 1 red means 3 choose 1, 4 choose 2 over 7-3. I'm getting 2 red would be 3 choose 3, 4 choose 1 over 7-3. I'm getting 3 red. Okay. So if I wanted, I can figure out the moment generating function. In this case, it would be e to the tk, e of x at k, which would give me e to the 0 power times 4-3 over 7-3. E to the 0 power, of course, is 1, plus e to the t, k now is equal to 1, 3-1, 4-2 over 7-3, plus e to the 2t times 3-2, 4-1 over 7-3, plus e to the 3t, 3-3 over 7-3. And this would give me some answer for the moment generating function. But it's not a nice, simple answer. Not a nice, simple formula. So the geometric distribution does have a nice, simple formula for the moment generating function. I can, if I wanted to, I could figure out the variance, but I just want to tell you something. I don't want to do all the algebra involved, but I want to make an observation. Remember, in this urn, I have R red. And N minus R other. So the percentage of red is just R divided by N. I want you to make an observation. Now, what I can show when I do it in the text, it's just a little bit of algebra, is I can show the following. I can show for the geometric distribution, it turns out to be a simple formula for the expected value. It just turns out to be NP, where P is R over N. And the reason this happened is, if you think about it for a second, when N is really, really large, there isn't much of a difference between a binomial distribution when you're drawing with replacement and drawing without replacement. And by the way, another result that happens for the geometric, don't memorize this, it's given to you, is this turns out to be NPQ times N minus N over n minus 1. So what this says, by the way, is an interesting result. It says for large n, a hypergeometric distribution approaches a binomial. In fact, I have an example somewhere that I want to illustrate. Where is that? Let me get my glasses on and see it. Yeah, let's suppose I have 100 marbles. I have 10 red marbles and 90 blue. And I draw 8 So notice there are a total of 100 marbles, and 8 is relatively small in comparison to the number of marbles there. Determine the probability. So 8 drawn without replacement. Determine the probability most 2 red are selected. So in most 2 red means what? None, 1, or 2, right? So what's the probability? Here's what we're asking. X is less than or equal to 2. So this means X is 0, or X is 1, or X is 2. If there are no red, well, firstly, I'm drawing from 100 marbles, I'm drawing 8. So here's my denominator. If there are no red, then all 8 are blue. If there's 1 red, 7 blue. There are 2 red, 6 are blue. And by the way, I just want to note the answer to this turns out to be 0.9686. Now, here's the observation I want to make. 8 is relatively small. The number of marbles we're drawing is small compared to 100 marbles. So does it really make a difference whether we're using with or without replacement? So let's suppose we approximated this problem by a binomial. Okay, so if we did it by a binomial, the probability that X is less than or equal to 2 would be B0, 8.1 plus B1, 8 0.1 plus B to 8.1, remember 1/10 is the probability of the success. And this turned out to be 96.19. So now let me make my point. My point is, if there are a lot of marbles in the urn, even though we're drawing with or without replacement, the fact that there are a lot of marbles, the difference is insignificant. We could approximate the problem by a binomial. Okay. So that's the hypergeometric. So the thing to remember about the hypergeometric is, if we think of R red in the urn, and there are a total of n marbles in the urn, and if I think of P as being R over n, then for the hypergeometric, E of x, the expected number of red, is just n times this P. And the variance, I forgot what I wrote before, was, what was the variance? NP cubed n minus n over n minus 1. There's nothing really new about the hypergeometric distribution. So now let's talk about another distribution. Anybody have any questions so far? Okay. So we have the binomial. We have the hypergeometric. So I now want to define the geometric distribution. This is a really beautiful distribution and has some really nice applications. So once again, I'm going to assume my experiment is, I can classify my experiment as success or failure. And the probability of success is once again little p. Okay, so I have essentially an experiment, and each time I think about the experiment, I either have a success or failure. And I'm assuming again Q, of course, is always a complement. Suppose further, suppose X is the number of trials required until we obtain a success. Our first success. X is said to be a geometric distribution with parameter P. Okay, so again, what is X? X is the number of successes. X is the number of trials we need until we get the first success. So the problem is, what's the probability that X equals K? What's the probability that it takes exactly K trials to get the first success? That's the question. Well, if it takes K trials to get the first success, what happened in the first K minus 1 trials? There must have been failure. So we must have the probability that X equals K. Since they're all independent events, we got K minus 1 failures. And then we got success, P, K equals 1, 2, and so on. So in order to get a success on the K trial, the first K minus 1 trials must have been failures. So by independence, it's the product of the individual probabilities. So what happened was we got failure, 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 and ultimately we got a success. Failure, failure, failure. So we had K minus 1 failures. And by independence, the product of the individual probabilities, we find the probability of success on the Kth trial just be Q to the K minus 1 times P. Okay, so if X is a geometric random variable, the probability that we have our first success at K is equal to Q to the K minus 1 times P. Okay. Now we've looked at geometric distributions before as well. Remember the dice problem on your exam, for example, was actually a geometric distribution. We'll talk more about that later, perhaps. So there are a couple of questions we'd like to answer. Namely, what's the expected value for this distribution? What's its variance? Well, we know we can figure out its moment generating function. Do I do that? Yeah. M of t is equal to e to the tk, or tx, doesn't make a difference. Which in this case, we have M of t is equal to the sum e to the t k. The probability is Q to the K minus 1 P. K goes from 1 to infinity. The trick is to write this a little differently. If we're a little bit clever here, we can do the following. Put another Q in here and divide by it. And let's take the P out. And now let's rewrite this as P over Q sum K equal 1 to infinity of e to the T Q to the K. This is a geometric series. Think of this as just being R to the K. So the first term is e to the T times e to the T Q over 1 minus R And if I simplify this a little bit, I get the geometric series M of t, the geometric distribution is P e to the t over 1 minus Q e to the t. Again, you don't have to memorize this. You'll notice if you look in the text, there's a table on page, where's that table? There's a table on page 165, and that's the table I provide you in your next exam and your final exam. It has all the information we need here. So I have the moment generating function. And now if we use calculus, remember, if I take the derivative of this with respect to t using the quotient rule, I end up with, I'm just going to give you the result, P e to the t over 1 minus Q e to the t squared. And I also get the second derivative, again using calculus, which is a bit messier. P e to the t, I'll let you verify this since you've all had a semester of calculus. 1 plus Q e to the t over 1 minus Q e to the t quantity cubed. And if you work all this out, lo and behold, you'll find E of x, which is m prime of 0, turns out to be very simply 1 over p. And v of x, I do the calculations in the text for you, turns out to be q over p squared. So we have the geometric distribution. So let me summarize. Probability that we get our first success at time k is q to k minus 1 p E of x turns out to be 1 over p. The variance turns out to be q over p squared. Consider the following example. A die is tossed. Determine the probability it takes at least 5 pluses before a 6 appears. Okay, so let's suppose I let x equal to the number of tosses before I get a 6. So the question is, what's the probability that x is greater than or equal to 5? Maybe I'll show you how to do this. Okay. So there's my question. Now, by the way, we know little p is 1/6, and q is 5/6. So the probability that x is greater than or equal to 5 is really the sum from 5 to infinity of q to the k minus 1 times p. Which, by the way, is a geometric sum. Remember, this is a geometric series. The first term of the series with k is 5 is this will just turn out to be 5 to the 4th over 6 to the 4th. I'll show you how to do this another way in a minute. And by the way, if I ask on average how many tosses are expected, that would be 1 over p, which is 1 over 1/6, and you would say 6. Now, there's actually an easier way of doing this problem. I want to make an observation. For a geometric series, the probability that it takes more than k successes means the first k successes were failure. So one can prove that this must be true for a geometric distribution. The probability that x is greater than k means if it takes more than k successes, if it takes more than k trials, the first success, that means the first k successes were failures. So one can actually prove this is an equivalent definition of the geometric distribution. I think I asked you to do that as an exercise. There's another property I want to talk about in a moment, but this one's pretty useful. So in fact, if the problem that I gave you a moment ago was the probability that x is greater than or equal to 5, you could have just said that just equals the probability that x is greater than 5 plus the probability that x equals 5. This would be q to the 5th, and then you can figure out that x equals 5. This one you can figure out immediately by yourself and get the answer. So that's just an observation. Okay. Now, there's another interesting property that I want to mention with respect to geometric distribution. I'm going to show you in a moment that the geometric distribution has what's called the memoryless property. That is, let me just say it and then I'll explain what it says. The probability that x is greater than k plus r, given x is greater than r, equals the probability that x is greater than k. Let's talk about what this says. Suppose, think of a fuse. Suppose a fuse lasts for 5 hours. What's the probability that the fuse lasts for another 5 hours? And this property says it doesn't matter what happened in the first 5 hours. That is, notice this result says the probability that x is larger than k plus r doesn't matter what happened before. So how do we prove this? Well, firstly, Notice I showed you a moment ago that this I claim is equal to probability. This is just Q. Let me work it. This is just Q to the K minus 1. So I need to show the left-hand side is equal to Q to the K minus 1. Well, how do I do that? Let's look at the left-hand side. This is equal to the probability of X greater than K plus R and X greater than R. Remember, it's the intersection divided by the probability of what's being given. Well, this is just equal to P of X to the K plus R over P to the X is greater than R. This is Q to the K plus R power. This is Q to the R power. And using my laws of exponents, this gives me Q to the K, which is the right-hand side. So we have this memoryless property. Interesting idea. One can prove, by the way, that the only distribution has this property, the only discrete distribution has this property, is in fact the geometric distribution. So this could be a defining property of the geometrical distribution. So if you think about a problem like we had on an exam, as we have a, I forget the exact problem, but suppose we toss a pair of dice, we have A and B. A goes first, they toss a pair of dice. What's the probability that A gets a 6 before B does or something? That's really geometric distribution. Okay, one more example here. Let me begin with an example. It's an example of what's called the negative binomial distribution. It's also called the Pascal distribution. But forgetting the name, and there is a formula in the text which I'll never remember. Let me do the problem and I'll show you how one handles such a problem. So a fair die is tossed. And the number of times and the number of threes is recorded. So we're tossing a die. Determine the probability that the seventh three occurs on the 11th toss. Okay, that sounds like a complicated problem. So I'm tossing a die. Determine the probability that the seventh three occurs on the 11th toss. Well, how do we handle this problem? And again, this has a special name, this kind of problem. It's called the negative binomial or the Pascal distribution. I never really remember the name. I just want to point out the important thing is how you do the problem. So here's the observation to make. If the 11th, if the 7th 3 is supposed to occur in the 11th toss, what does that mean? That means in the first 10 tosses, we must have wait a minute, 7. We must have 6 successes. So what's happening is in the first 10 tosses, we have 6 successes. And success on the 11th toss. Remember, these are independent events. So there are really 2 parts of this problem. I have to get 6 successes in the first 10 tosses. And on the 11th toss, I have to get a success, and the probability of success is what? 1/6? This is just 1/6 by independence. Okay, now this is just an ordinary binomial distribution. Binomial distribution. We want 6 successes in 10 tosses, and the probability of success is 1/6 times a success on the last toss. So what does this give me? This gives me 10, choose 6, 1/6 to the 6th, 5/6 to the 4th, times 1/6, and this gives me just 10 choose 6, 1/6 to the 7th power, times 5/6 to the 4th power. So I actually solved the problem of this negative binomial or Pascal distribution. In fact, I can show even more. I can show if I can actually find its mean and its variance. So in this case, what I call 7 times is m times. One can show that for the Pascal distribution, it's a generalization of the geometric. Maybe I'll do this the next time because I'm running out of time. E of x will turn out to be m over p. In this case, m of 7. And one can show v of x is, I'll do this the next time, m cubed over p squared. Pascal. Don't worry about this now. I need to derive this. I don't have enough time to do that today. So Pascal. I just want to remind you of some other things I'm going to need soon. Some results from calculus. Notice we're already doing some differentiation when you're taking the moment generating function, you're finding a derivative. Again, that's important. Let me just remind you, remember the moment generating function, the first derivative of the moment generating function gives us the mean. And the second derivative, evaluated at 0, evaluated at 0 of the moment generating function gives us e of x squared. So we're already doing a little bit of calculus. And now I want to remind you of two more results from calculus. One of them we've already done, but we're going to need this very shortly. When we talk about that, we're going to talk about the Possum random variable. So the results from calculus I want to remind you of are the following. The first is e to the x can be written as a series, an infinite series. And this is true for all x. So this is going to be 1 plus x plus x squared, 3 factorial, plus x cubed over 3 factorial, and so on. Take this as a fact. And the other fact that we're going to need is the following limit: 1 plus lambda, 1 minus, I think I use minus. Lambda to the n raised to the n power. We'll take the limit of this as n goes to infinity. This is equal to e to the minus lambda. You're probably more used to seeing the result in the form of 1 plus 1 over x to the x. This limit approaches e to the x. But I much prefer this form for what follows next. Now, these two results are fundamental results from calculus. I'm going to assume that we're familiar with them, and I'm going to use them as I develop one more distribution called the Possum Distribution. Okay, this is probably the best place for me to stop right now. So let me stop the recording. Again, this will be posted tonight. Let me. Okay, take off my glasses so I can see again.